Alright, got a G-Stus. Well, here's Ardu-Bot-Tom, and now we're gonna see what he can do. Basically, there's 4 basic movements: forward, back, left, and right. The left and right movement are depicted by this servo, as so. And the forward and backwards movement are basically done by the gearbox motors. And there you go. Forward, backwards, left, and right. And that's pretty much what Ardu-Bot-Tom does. It's pretty fun. Alright, let's move on to the construction of Ardu-Bot-Tom. So for the construction of Ardu-Bot-Tom, the frame for the whole robot consists of a universal plate set from Pololu, and basically what we did here was we pulled out the plate and attached a Arduino Uno board to it using double-sided tape. Then we attached a battery using also double-sided tape. This battery feeds the microcontroller using a 9-volt battery adapter for the Arduino. The antenna was created using shrink wrap, just regular shrink wrap, and a piece of black wire. Make sure the antenna is at least 11 centimeters long. It's necessary for our modules to function correctly. Both tires, both front tires and back tires, came in this box right here from Pololu. It's an off-road tire pair. You can get all these parts at our website. At the bottom, you will see that there's a 3.5 by 2 inch white breadboard. This 3.5 by 2 inch white breadboard you can get at our website also. It's the Pololu breadboard, and it will come in a package just like this. And as you can see, there's a battery, and this battery is basically what gives power to our servo, which is up here, and our gearbox. The gearbox is attached using bolts and nuts that come with the kit. The box looks just like this. It's a twin motor gearbox. It is a little bit complicated to put together, and that's why, and as part of this tutorial, we added a few links for basically the assembly instructions, or actually a modified version of the assembly instructions. Will help you. It'll help you assemble this gearbox correctly. The servo motor was attached, like I said, using zip ties, and to actually attach the axle that holds the 2 tires, we had to use the following 2 parts. This, which comes in a little baggie inside of the SparkFun Inventors kit with the servo, and this, there's actually 2 of these that come inside of the universal plate set. And basically what we did was we glued this plastic piece right here, 1 on each side, and then attached this to our servo, and now we have an axle. All you have to do now is put the axle through the little hole and out of the other side also, and there you go. Attach the tires and you have a front axle with tires that freely spin, just like this. There we go. And this breadboard has an adhesive in the back, like I said, that attaches to the plate set. And to control the gearbox, the Arduino has a little problem, and the problem is that it can only source out about 20 milliamps of current. That is not enough to run the 2 motors on our gearbox and the servo, which controls the left and right movement. Therefore, to run the gearbox motors, we used this module, which is right there. As you can see, it's right there. And this module will give us the currents necessary to run the two motors off of a 9-volt battery. And for the reception of the signals, from the controller, we used one of the link kit pairs, the receiver from the link kit pair. And the pair looks like this. And this one will go to the controller, and this one will go to the vehicle itself. So there we go. That is the whole construction of Ardu-Bot-Tom. All these wires that you see connecting everything are also part of the SparkFun Inventors kit. So basically everything you need will be included with the parts that we have discussed and the Inventors kit. Now let's move on to the controller. The controller's interface is a lot simpler. The first main part is the body of the controller. The body of the controller is composed of the breadboard that comes as part of the SparkFun Inventors kit, as you can see in the front cover of it, right there. Then we have our Arduino Uno. The way the Arduino Uno was attached on the bottom was using double-sided tape. Another alternative to that is that the bottom of these boards always comes with an adhesive. You can take this adhesive off very easily and then just attach your Arduino Uno on the bottom right there. Or you can just leave it on there and put new tape on there like I did. And then for actually generating the codes, we have a SparkFun joystick. And to provide power to the whole thing, we used a 9-volt battery. To connect the 9-volt battery to the Arduino, we use this wire. This basically it's an adapter, a 9-volt battery adapter for the Arduino. And the antenna was created the same way that we created the antenna for the vehicle, using shrink wrap and a piece of wire. Again, make sure that the piece of wire is at least 11 centimeters long for the transmitter module to be able to send the code correctly. And finally, the transmitter module. Transmitter module is the same one that I showed you earlier, and it comes as part of the kit. There it is. And basically that is the whole interface for the controller that will control our vehicle. The general idea of this is that when you move the joystick, it will send an analog value to our Arduino through these wires, and the Arduino will read those two analog values and create a code depending on the values, and that code will represent which way you want your robot to go. Then that code is going to get sent through this wire out to the transmitter module, and the transmitter module will send the code out through our antenna, and our vehicle will receive it and do accordingly. Alright folks, now let's have a look at the code to control Ardu-Bot-Tom. The first thing you may notice is that there is a library included here, and this library basically just has a type def enumeration with 5 possible directions that your robot could be traveling: nowhere, forward, backwards, left, and right. And then we created 2 instances of this type def enumeration with the names robot direction and current underscore direction, or cur underscore dir. And we're going to use this type def enumeration in the actual Ardu-Bot-Tom sketch to control the direction of our robot, depending on the codes that we receive from the controller. The first thing we're going to do is we're going to include that library that we just included here. And we're going to include the servo library because we're going to need it to move the servo that's going to be controlling the left and right movement of the robot. Then we're going to create 5 different variables. The first 4 are going to be the pin numbers that the motor controller board for the gearbox motors is connected to. So pins 2, 3, 4, and 5. And we're going to create one more variable, which is the position variable of the servo, and we're going to initialize it to 90 degrees because we're going to pass this to the servo initially in our setup function to make the servo face forward. Then we're going to create a servo object and a current direction variable, and this current direction variable is going to derive from our type def enumeration that we created here, as you can see right there. And the idea is that we're going to have two function prototypes, move gearbox and move servo. And the idea here is that we're going to pass this current direction, whatever it is, to move gearbox and move servo, and these two functions are going to take care of actually moving the actuators, the gearbox and the servo. The robot direction and current their type are both the same thing. Again, they both derive, they're instances of the type def enumeration that's in the library. So we're going to pass this to here and this to here, and depending on what it is, they're going to move respectively. For the setup function, the first thing we're going to do is we're going to initialize the serial interface at 4800 baud. The reason we pick 4800 baud is because the transmitter and receiver modules that we're using are rated for 4800 baud. And then we're going to set all the motor control pins, motor A pin 1, motor A pin 2, motor B pin 1, motor B pin 2 as outputs. And the reason we're going to do that is because we're going to have to send codes or pulses, either low or high pulses, to these pins to control their direction. And then we're going to attach the servo object that we had just created to pin 6, which is where our servo is physically connected. And once we attach it, we're going to write the position value, which is 90 degrees, and this is going to basically face our tires forward as soon as we put power to the Arduino. And we're going to set the current direction to nowhere because we don't want our robot to start moving unless we push the joystick on the controller and codes are actually being sent and received. In our loop function, the first thing we're going to do is we're going to check if the controller is actually sending us codes. And if it is, we're going to read those codes and we're going to compare them to the following 4 different possibilities. Code F, B, L, and R. Forward, backwards, left, and right, respectively. And if it's F, we're going to set the current direction variable to forward. If it's B, we're going to set the current direction variable to backwards. If it's L, we're going to set the current direction to left. And if it's R, we're going to set the current direction to right. If it's none of the above, then the default case will execute and it will set the current direction to nowhere. And then now that we have a current direction established, we're going to pass that to the move gearbox and move servo functions. And we're going to have a look at these two functions right now to see what they're actually doing with this value. In the move servo function, we're going to create an integer variable that's going to represent the speed of our servo. Then we're going to check if the current direction is left and the position is greater than 0 degrees. 0 degrees would be if the servo was turned all the way counterclockwise. So basically what I'm saying here is if the direction is equal to left and the position is not all the way counterclockwise, then we're going to decrease the position by the servo speed variable, which is 4. So position is going to get decremented by 4 every time if we're receiving the code for left and the position is not all the way left yet. If the direction is right and the position is not at 179 degrees, which is all the way clockwise or all the way right, then we're going to increase the position of the servo by the servo speed, which is 4. So if we're receiving the code for the servo to turn right, so R, and the position is not all the way to the right, then we're going to increase the position by servo speed, which is 4. It's going to increment by 4. If the direction is not right and the direction is not left, then the position will stay the same, and this will basically not move the servo at all. Finally, now that we have a position established, we're going to write that value to the servo, and this line right here will take care of actually physically moving the servo for us. On the move gearbox function, we're first going to basically check the variable that's being passed to it. So If the direction is forward, then we're going to turn motor A clockwise by sending a high pulse to motor A pin 1 and a low pulse to motor A pin 2, and we're going to keep it going clockwise for 15 milliseconds. And then we're going to turn motor B clockwise by sending motor B pin 1 a high and motor B pin 2 a low, and we're going to keep it like that for 15 more milliseconds. The reason we split both motors into their so they spin individually is because if we were to spin them both at the same time, then the total current output of the driver board will get split in between both the motors, and we don't want that. We want the full current to go to both motors individually, so that way we can have the maximum speed possible and the maximum torque as well. And then we check if the direction is backwards. If the direction is backwards, then we switch these two, and we, instead of sending a high to motor A pin 1, now we send a low to motor A pin 1, and we send instead of a low to motor A pin 2, we send a high to motor A pin 2, and this will instead turn the motors counterclockwise, or left, or back, and then we're gonna keep it like that for 15 milliseconds. And do the same thing with motor B. Motor B pin 1 will send a low, motor B pin 2 will send a high. We'll keep it on for about 15 milliseconds, and then this will take care of moving our vehicle backwards. And finally, if the direction is not forwards and if the direction is not backwards either, then we're going to send a low pulse to all the control pins, and that will prevent our motors from moving. And there we go, folks. That is pretty much the whole sketch for Ardu-Bot-Tom. Now let's go take a look at the controller sketch, so we can have an idea of how the codes are actually being sent to the vehicle. Alright, folks, so this is the code for the controller. First thing we're going to do is we're going to create a couple of variables, and the first two represent the pins that the joystick is connected to, so analog pin 0, analog pin 1. It's two axes, vertical axis, horizontal axis. And we're going to create two variables to keep track of the vertical axis and the horizontal axis. And we're going to create two more variables to store the 0 point. So as soon as the microcontroller gets power, it's going to save the current point for the vertical and horizontal axis, and it will save those two as 0 points. So basically we can keep track of when we don't want any movement. So if the x-axis, the vertical and the horizontal axis are both at the 0 points, then our joystick is not moving. We don't have our finger on it because it's back to the original position. Then on the setup function, we're gonna initialize the serial interface at 4800 baud, just like we discussed during the Ardu-Bot-Tom sketch. And then we're gonna read in the vertical 0 and the horizontal 0 values, and we're gonna map them to 0 to 1023. And on the loop function, we're gonna read the vertical value and the horizontal value, and we're also gonna map them 0 to 1023. And these values are going to be read from the vertical and horizontal pins. So it's going to be analog pin 0 and analog pin 1. Then we're going to create some new variables, integer variables. One's going to be the forward value, the backward value, the right value, and the left value. And here, what we're basically going to do is we're saying if the joystick is pushed up past the 0 point and plus the offset value, then store the distance up from the 0 point and clear any previous distance from the bottom side. Same thing with this. If the joystick is pushed down past the 0 point minus the offset value, then we're going to store the distance down from the 0 point into the back value. And then we're going to clear any previous distance from the top side, so the forward value will be equal to 0. Then we're going to find the distances from the 0 position, and plus or minus the offset value for the left and the right. The way we're going to do that is we're going to say if the joystick is pushed left past the 0 point plus the offset value, then we're going to store the distance in the left value, and we're going to clear out the right value.
And if the joystick is pushed right past the 0 point and minus the offset value, then we're going to store the distance right from the 0 point, and we're going to clear out the previous left value. Then we're going to find the largest of all the 4 values that we just read in, and that is going to be the direction that our joystick is pushed. And then we're going to say if forward is the furthest one, then we're going to literally write that into the serial interface, and that's going to send it out to our transmitter module. And then we're going to send this to the serial monitor, so we can keep track of which direction we're moving. So we're going to say controller moving forward, you know. And then same thing with the backwards value. If the backwards value is the greatest, then we're going to send a B through the serial port, and we're going to send this message to the serial monitor to know that we're moving backwards. Same thing with the left value. If it's the greatest, we're going to send an L, and we're going to send this message to the serial monitor so you can keep track. And for the right value, if it's the greatest, we're going to send an R, and we're going to print this on the serial monitor so we can keep track. If none of these evaluates the truth, so in other words, if you're not pushing your joystick anywhere, then we're going to send a U. And the reason why we're going to send a U is because a U in ASCII coding basically represent a series of zeros and ones, so 0, 1, 0, 1, 0, 1, 0, 1. And that will help us to keep synchronization in the transmission line between the controller and the receiver, because there won't be too many consecutive zeros in the line, so the clock will stay synchronized. We need transitions in the line in order to keep the clock synchronized, and that's why we send a U, because then we have 0, 1, 0, 1, 0, 1, 0, 1, and it keeps the clock synchronized. And then we're going to send this message to pretty much let you know in the serial monitor that we're not moving. Well, folks, there you go. That is the sketch for the controller, and that's how the codes get generated and sent out. Alright, let's move on. Alright, folks, we hope that you enjoyed the Ardu-Bot-Tom tutorial, and we encourage you guys to follow our links and leave us any comments if you have any.